Right, so we now have arrived at the last point of the program. It's a presentation by Simon Wakter, who's senior advisor with AFRY. He's the co-author, together with Staffan Quist, of a report, a forthcoming report around this very theme, nuclear beyond electricity. So please, Simon, the floor is yours.
Of course, alongside this conference was a report commissioned by Energiforsk on the same subject called Nuclear Beyond Electricity. And a lot has been said already now in this conference, so I guess I will use this opportunity to try and summarize. The report will also be made available as a popular science brochure afterwards. So yeah, I advise everyone to have a look at this report once it's made available. The presentation will be made available also as a popular science report. This presentation I originally intended as an introduction to this conference when it was still scheduled in person, but I'll take this opportunity instead to try and summarize what was said during these days. And I also help Marcus a bit with his job, so he doesn't have to try and summarize everything that was said. But before we get to the summary, I think I'd like to step back a little bit, remind us a little bit why we are looking at this, why we're all engaged with this, and then also do a bit of a rewind to put things into perspective and see if there's anything that we can learn from history that is relevant here. I think we all agree that we face some massive challenges trying to decarbonize society on this decarbonization journey. And we face a increasingly pressing urgency in the climate challenge, which demands swift action to address and drastically reduce carbon emissions, which are currently still increasing. And this chart shows carbon emissions by economic sector as defined by the IPCC. If we recolor this chart a little bit creatively, we can see that energy constitutes a very large part of the global carbon emissions. If we rearrange this in another way, it is clear that the climate challenge really is an energy challenge. Energy is at the heart of the climate challenge, but this also means that energy is at the heart of the solution to the climate challenge. This is, of course, also why the work of Marcus and the people at Energiforsk and all other people engaged in energy, why that work is so important. And within this energy space, nuclear actually already plays a very significant role. Nuclear provides a significant part of electricity globally. I won't read all of the stats here, but a significant part of fossil-free electricity, especially in developed economics. All of this from only approximately 440 reactors. Unfortunately, despite our best efforts, or maybe not our best efforts, but some effort, progress on decarbonization is still painfully slow. The share of fossil fuels in electricity basically hasn't moved at all in the past 20 or 30 years. And the situation is similar if you look at total energy, except then the share of fossil fuels is closer to 80% instead of 60%. And the reason why 1997 is chosen for the comparison here is because it's the year the Kyoto Protocol was adopted. I should add that with newer data for 2020 or 2021, the share has actually moved a bit, but it doesn't make the chart as interesting. And in this same time, since 1997, global electricity demand has more than doubled. Global energy demand has increased more than 50%. And so it is clear that clean electricity supply has to increase dramatically. And this not only globally, but also in the Nordics, because although our electricity here is fairly clean already, especially if you look at Norway and Sweden, where I think you can say it's already fossil-free, demand for clean electricity is set to increase dramatically as we transition away from fossil-free transition to fossil-free fuels. In Sweden, the electricity demand is estimated at 310 terawatt hours by 2045. This is an increase of 170 terawatt hours. If you take into account the production that will retire, and depending on whether you think the nuclear units will be operating or not by then, we're looking at 200 to 250 terawatt hours of new production. In Finland, it looks similar, slightly smaller numbers, but equally daunting task. An increase of about 50 terawatt hours from today, And these numbers are still quite conservative. And with this increase, we do not meet the net zero targets. So on that, I think we can pause for a second to realize that this is a very significant challenge, meeting this electricity demand, the increase that is required. And then before we move on, I'd like to do some historical reflections on this, because we looked into a lot of different topics, but we don't have time to deep dive into all of them. So this is the high-level takeaway from this report. So for this purpose, I'd like to set the scene in Sweden. We rewind all the way back to just after the Second World War. So Sweden had been steadily electrifying, expanding hydropower during the Second World War, especially up until 1942, where it stopped a little bit. And then, however, in 1947, 2 years after the end of the war, disaster strikes. Sweden faced three major problems at the same time. Demand growth for electricity was higher than ever before, following somewhat of an economic boom after the war. This came as a surprise, as energy demand after the First World War actually decreased significantly. There was also the expansion of new power stations and power lines was behind schedule, in both short term and long term. And 1947 was a year with an exceptional drought. So the problems faced in 1947 were serious. And this nice little helper on the side is called Kalle Watt. And he was the electricity rationing advisor, advising people to pull out the plugs. So 1947 is one of the driest, if not the driest years on record. It is the longest documented period without any rain that happened in this period, where the area around Skövde went without any rain for 65 days straight. There were several heat records that still stand to this day, 38 degrees in Målilla. And then electricity rationing in the autumn reduced consumption by around 20%. The problems were kind of compounded by urbanization. Sweden was changing rapidly, people moving to cities because that's where you could find jobs. So demand for both electricity and heat were increasing dramatically, and so dramatically that people quickly realized there was a real risk that there could be a shortage of both within a few years. So how could more electricity or heat be produced? Well, the answer to that question is district heating. And district heating came to work both as a bit of an insurance policy and a diversification of the energy policy. So there was no doubt at this time that hydropower resources were fundamentally limited. They were not infinite, and they could not be expanded quickly enough to meet all of the demand growth. And hydropower was also subject to these spells of drought. So district heating became the insurance policy against drought years, and it was also a central part of diversifying the energy strategy to be able to meet the growing demand. And this is also the time where Sweden's first municipal district heating system starts in Karlstad in 1948, which delivered heat and electricity to a mechanical workshop and then later to some apartments. At this time was also the foundation of the Atomic Committee, and in 1947 AB Atomenergi was founded. So there was a great realization here that there was a need for more solutions than just one. However, the drought years were a recurring problem. So Sweden would go on to experience several more drought years, first in 1955-56, and the situation started looking dim again. This was made worse by the Suez crisis, which cut fuel supply to the district heating power plants. The situation was then saved a little bit, remedied by lots of snow and rain, which eased the situation. And it filled magazines to the fullest level ever. And now people thought that everything was fine and dandy. However, the following months just after that were exceptionally dry, and Sweden once again found itself in a drought. The new power plants now had to cover about 30% of consumption, which set a new record. And thanks to this and some voluntary demand management, the situation was managed. And the image here shows Kalle Watt thanking people for saving electricity, managing the crisis. However, 10 years after this, in 1970, the unthinkable happens. Sweden experiences 2 severe drought years in a row. And Lennart Lundberg, then vice president of Vattenfall, describes these years as a real lesson for the whole industry and something which made everyone reevaluate what they thought was previously true. And so statistically speaking, 2 drought years in a row like that is thought to happen about every 30 years. And for the first time since 1947, they once again had to ration electricity. So why is this of relevance then? Well, because I think today's situation is not entirely different from then. We have rapidly increasing electricity demand, also within some new areas, as we see electrification or new energy carriers like hydrogen, replacing legacy fossil fuels. We see sector coupling, new consumption patterns, the build out of district heating in response to shortages was also one type of sector coupling back then. We also face possible shortages today and situations with scarcity. And this could be not only potential shortages of electricity, like electrical power or electrical energy, but also in terms of transmission capacity or access to grid connections, which become like a scarce resource when many people or projects want to access them in a short amount of time. There's also a growing concern over materials with cost increases recently on many commodities, which has resulted in increasing costs for batteries, solar panels, wind turbines, lots of products affected. And in the 40s and 50s, it was the rise of the national grid that made these problems that were before local problems, they became a nationwide problem. Today we have global markets where a drought in Brazil feeds a spike in LNG prices in Europe. And there are also many other factors, of course, many uncertainties and dependencies, like our neighbor in the east, access to fuel, certain gases fuel, and how that has impacted energy prices. So I like to reiterate that energy is at the heart of the climate challenge, but this is also the solution to the climate challenge. And there's been a lot of talk about electricity, but quite enough for now, because electricity is only a very small part of energy use. Heat is the largest energy end use of all. Electricity makes up about 20%, heat makes up about half. So heating for our homes, industry, other applications accounts for half of all energy consumption. It contributes about 40% of global carbon dioxide emissions. So of this heat, you can show briefly, of this heat, half is for industrial processes, about another half is, half is space and water heating, a little bit for cooking, about half is industrial processes, and a little bit is used for agriculture, which is essentially heating greenhouses. So out of all of this, if we summarize the urgency of addressing emissions, while also taking into account the challenge of this rapid demand growth, new and changing patterns of energy use, trying to address these security supply issues, together with the enormous role that heat plays in our energy consumption, I think against this backdrop is where this report comes in. And that also motivates several of the research aspects of the report. So this report is split, you could say, into 2 parts, one with the background, that covers initiatives and activities that are ongoing, for example, IAEA, AFRY, INL, and others, some of which we have heard from during this conference, excellent presentations. Also covers technology and nuclear heat, as a brief introduction for those not familiar with nuclear reactors and the potential of nuclear heat. Also covers steam extraction, was a brief addition at the request of the project reference group, which asked for a brief analysis of steam extraction, primarily from existing power plants. A number of different applications were investigated, like district heating or desalination. Then we had some more detailed investigations, and that was into direct air capture, as Staffan Quist presented yesterday. Also looked at hydrogen production, looked at integration of SMRs in steel production and uses for existing power plants. So we'll take a very brief look at some of these uses now. So first of all, Nuclear reactors produce heat, and they produce lots of it. More than anything else, the real strength of nuclear is that it provides very large amounts of heat at very competitive prices. So this image shows ranges of heat required for different processes, as well as the heat output of today's existing fleet of reactors and new reactors. If you look at steam extraction from some plant, this schematic shows a typical second generation BWR plant. And circled in orange with the text descriptions, also in orange, you see the possible steam extraction points, the dashed orange lines there. In addition to these extraction points at the bypass valve, at the preheater or after the reheater before the low pressure turbine, it's also possible to extract steam from the low pressure turbine, or also if you through more modification, if you have a back pressure turbine configuration, you can extract more power. So these will take increasingly more modifications, and Staffan presented more on this already yesterday, and there's more content in the report, so we will not spend too much time for this, but you could extract some, perhaps 10% without too many modifications, and significantly more the more you're willing to modify your plant. District heating was one of the topics looked closer at, and of course, district heating is a use that is especially relevant in the Nordics. We have a lot of district heating, and it's an interesting area. So I want to show some slides on this. This chart shows district heating supplies from Hellenoi, the power company which supplies 90% of Helsinki with district heating. And as you can see, output is highly variable, high annual variability, but there's a stable supply trend. It was growing in Finland. It's been stable in Sweden for a few years, now also stable in Finland since a few years. If we reorganize this data into a low duration curve, I think you can also see from this picture if it doesn't change. You see that winter loads are about 10 times higher than summer loads. So this is a significant barrier for a reactor, which is capital intensive. You want to use it as much as possible. You want high utilization factors. Anyway, that's a significant barrier to nuclear units, which you want to run as much as possible. The potential market for district heating is determined by the amount of full load hours and at what power you have these full load hours. So you need quite big markets. So seasonal variability is a problem. The market demand depends on how many full load hours you have at what demand. So there are only a few cities that can actually accommodate a reactor because it's quite a large output. And but estimates for the cost of this are quite favorable. So for cogeneration, there are estimates showing 20 euros per megawatt hour. That is very competitive. And for pure district heating reactors, around 30 euros per megawatt hour. The next topic is desalinations. There are different types of desalination. Won't dive into them because they're covered in the report. With the trouble there, we tried running out of time a little bit. We looked into electrolysis. There are different types of electrolysis, low temperature electrolysis, PEM and alkaline. We heard about this from Jörg yesterday, and the most suitable one that we found is high temperature steam electrolysis. Offers a lot of benefits. So when it came to looking at the integration of SMRs in steel production, we're kind of diving through this now, but there will be more descriptions than this in the report. So this shows integration of SMRs in steel production. I will actually try and spend a second on this slide to show it. So this shows integrating high temperature gas reactors. They have an output of approximately 750 degrees. This is a very generic schematic, so but trying to illustrate the process. That outputs steam, which goes both to turbines generate electricity and steam to the high temperature steam electrolysis. And from that steam electrolysis, you get hydrogen and carbon monoxide, because we have carbon dioxide, which we buy from somewhere. It's too expensive to capture it, so we by it. The problem is that this has to be fossil-free somehow. You feed both hydrogen and carbon monoxide into the reactor for the reduction of iron ore or iron pellets. And there are several considerations to this process that are quite difficult to weigh in. This also depends heavily on how your plant is integrated at the location where you are sited, what your customer demands in terms of product. For example, who adds the carbon to the product, and have you also integrated with like an electric arc furnace at the end here to produce steel all the way? We say we integrate this with steel production, but actually we stop here after we produce hot briquetted iron. So that's our final product in this analysis. This process recirculates a lot. You have to feed the process a lot of hydrogen, about 3 times more than it actually requires for the reduction of the iron. So that hydrogen is recirculated, and then we burn it again, because if you burn hydrogen and oxygen, you just get steam. And that is fed into to raise the temperature to the temperature that is actually suitable for the high temperature electrolysis, because the output from the reactor is not quite high enough. And the spray cooler here are to lower the temperature, because if you run the turbine at more than 605 degrees, you run into all kinds of little troubles with having to add more expensive elements like nickel into the turbine. The final bit is we look at existing power plants and what they can do. Of course, you can do some kind of modifications to extract steam for different purposes, but what we looked mainly at was the kind of ancillary services that you can provide. And I think with that, I'm finished. Some takeaways from this: I think there's a significant role for nuclear to play also in heat, as it does already in electricity today. And for 3 different reasons, I would say. We see the planned deployment of SMRs now in the near term. Not sure that all of these SMRs design will make it, but there are a lot of projects already before 2030. I would not be surprised if we start seeing kind of winners in the next 5 years, the ones that start getting contracts. I think that deploying more strategies is a great way to de-risk the decarbonization, especially difficult sectors as decarbonizing heat. In some high temperature sectors, I don't think that the catch-it-all hydrogen option is credible always. So in some applications, maybe nuclear is the only credible non-carbon option. But a lot has to be done to realize this potential. So nuclear can help ensure this orderly transition, which has not been so orderly in the past year. But it needs an environment that encourages it. And so with the right enabling environment, I think we can do a lot. A lot of these technologies are actually not new. They've been demonstrated separately, maybe not together always in large projects, but for example, district heating has been demonstrated. So it can be done. And with that, I say thank you. I'm not sure we have time for questions now. Sorry, Marcus, for the trouble with the presentation. Maybe we can take one question if there were any.
Yeah, thanks, Simon. Well, first of all, I want to encourage also the audience to look at the report. It's going to be up soon on our website. But and we, as you said, we need to wrap up. I want to ask you just one question. As you've sort of gone through this topic, out of the different applications for nuclear that go beyond electricity, which one do you think is the sort of the most relevant for the Swedish context in, say, the next 15 years?
That's a very good question. Yeah, we didn't quite have time with that because we got stuck a little bit on the district heating slides. But what I wanted to mention there was actually that if you are a mid-sized city, you're maybe running out of electricity now, because that's a problem that a lot of cities are facing. You can't have any more deployments. Maybe you can have large infrastructure logistics centers, not such exciting jobs maybe. If you want to deploy more exciting things like industry, you have to have electricity. You probably also have an old combined heat power plant that you have to reinvest in. And if you are reinvesting in something now to burn biofuel or waste, then both the cost of those, because I think there will be more competition for biofuels. Waste looks a little bit unsure how much it will cost for tax reasons and other reasons. And also emissions. So if you build a plant today, you will probably overshoot a little bit on scrubbers for that plant, and it's not sure that this will be. So if you start looking at it now, 5 to 10 years, you want to build it. It takes another 5 to 10 years. I think you look at 10 to 15 years when you have that new plant to replace the one that you want to phase out now. 10-15 years is not an unrealistic timeline, I think, with the right environment to replace that with an SMR instead, if you can accept maybe 15 to 20 years.
So are you saying that district heating is sort of the main, do you think that's the main application beyond electricity, or is hydrogen production, as you outlined in your slide, is that equally interesting, or if you had to choose one?
Well, I think hydrogen production as well, because I think we'll run into problems with the grid as a resource that is facing some scarcity. But the one that I see most likely to be deployed in the short term is probably for district heating, I think.
And then my final question, just briefly, do you think that sort of SMR is that sort of a requirement to realize the potential of these applications beyond electricity, or could we see large scale plants, either existing ones or even new ones, being used?
The demand for some of these industry projects is so enormous that it wouldn't be wrong to have a large reactor, but for district heating purposes, it would be difficult to find a demand for that. But you could build the lines, and something that's quite interesting is if you build really large district heating pipes, they actually don't really lose. You can build them for a very long distance because they don't really lose heat. But because you have to have the pumps for the journey, you actually end up with a higher outlet temperature at the other side than you put into it, because you have the losses from the pumps and the friction. So yeah, but I don't think we will see any big plants in Sweden anytime soon.
Okay. Yeah, thanks, Simon. Fascinating work that you've done. And thank you also, Simon. You've been instrumental in putting the program for this conference together. Just like to take the opportunity to thank you for that as well. Thanks a lot. And of course, thank you to all of you who've been listening in to the conference. I hope that we've succeeded with the objective that we set out and that I talked about yesterday, of sort of broadening the discussion around nuclear to not only sort of focus on replacing or expanding electricity production in the system that looks sort of similar to what we have today and perhaps envision for tomorrow, but also go beyond that and sort of acknowledging these much greater and closer couplings between sectors and applications that we who are working with the sort of scenarios for the low carbon future envision to be instrumental in that. So I think that this absence of those aspects from the debate and discussions around nuclear is somewhat problematic, and I hope that we've at least a little bit contributed to rectifying that. So with that, again, thank you very much for joining us. Don't forget to check in on our website for the presentations, and I'll see you hopefully next year.